Hello, welcome everyone. So in our lecture series now we are seeing about the importance of biosensor and the current trend and as well as future directions. So in this series already we discussed the importance of biosensor and then types of classification of biosensor. So mainly the biosensor can be classified based on the different types of transducer. We have transducers a main role to transmit the signal from the biorecognition event and transfer it into the analytical output into the measurable signal. So the transducer role is mainly important in any biosensor. Based on the transducer, we can classify the types of biosensor. For example, if you use electrochemical transducer like amperometric, potentiometric, cyclic voltammetry, or pulse voltammetry. These are the technique we are using in the electrochemical biosensor. Similarly, if you use optical based transducer, which is called optical biosensor. If you use mass based biosensor, which is called piezoelectric biosensor. So currently piezoelectric biosensor is a potential uh, useful for the current trend and future application because of it has a unique property and fabricating a self-powered biosensor devices for wearable applications. So now and then also we have discussed about the commercial, what are the sensor has been commercially available, especially in the DNA sensing technology. There are different company has been commercially developed a sensor for the detection of more than thousands disease related DNA sequences detection. But this technique based on fluorescence take DNA probe has been used for the DNA detection. However, the electrode fabrication, the sensing technology, all are the involve sophisticated instrument and involve a high large space places and the measurement and the detection process need a lengthy time and high expensive instrument to detect this analyte. So in order to alternatively to bring the low cost and eco-friendly biosensor, there are different approach has been nowadays they are developing. So among the different approaches, these piezoelectric based sensors currently mainly focus because it has several advantages. A simple working principle and can be easily monitor or tunable signal based on the material property. We can fabricate the electrode even flexible, stretchable. There are different approaches we can see. So in the following slide, we will see how this piezoelectric and triboelectric based sensor we can develop for our future applications. This one in previous lecture we can discuss the importance of nano generator. So it is simply convert the mechanical energy or physical changes into the electricity. The electricity is useful or benefit for the detection of small biomolecule or macromolecule or some food related molecule. There are different application we can use this small changes of electricity based on the piezoelectric, triboelectric and pyroelectric nanogenerator. So in this direction, especially how this piezoelectric material or this nanogenerator can be used for the fabrication of different types of biosensor. What are the methods we are using or how we can apply this methodology effectively to develop a different type of sensors. See here, this is the schematic diagram for the how in conventionally the self-powered biosensor we can design because this is signal output and then energy storage device which has been coupled with a nano generator. So already we know the principle of nano generator when applying some some mechanical force it generate a electricity. So similarly, that generated electricity can be stored in a energy storage switch, which is called the ultra supercapacitor or micro supercapacitor. Whenever energy is required for the sensing operation, we can bring from, or we can collect from this energy storage device. So internally it is inbuilt with here. So which means that in between we are using some separator. The separator acts as a energy storage device. So this is a dual application we can use for the nano generator as well as energy storage devices. So which is called a self-powered energy generator, energy storage devices. So this device we can directly apply for the uh, some uh, some operating some sensor and detecting some molecules, many things. So for example, how we are fabricating this nano generator. So here they have taken a titanium foil because we need some conducting substrate, so it should be stable. So here they have taken a titanium foil, and then zinc oxide nanowire has been grown vertically grown over the titanium pile. So there are different approach we can apply for the growth of zinc oxide nanowire because zinc oxide is a very basic and a powerful piezoelectric material and widely used for various applications. So the first step, the titanium pile over the titanium pile, zinc oxide has been grown vertically, either by hydrothermal approach, chemical vapor deposition, or physical vapor deposition, and also different salt gel method, lithography also we can apply. But this is a simple fabrication. Here they have been used for the hydrothermal approach for the vertical growth of zinc oxide nanowire over the titanium file. Followed by uh, they have coated with the aluminum foil as well as a Kapton. Kapton is like it is a insulating, does not have any conducting property for the Kapton. So it is cover the this whole fabricated device. It is like a sandwich. So the bottom zinc oxide, the bottom titanium foil, in between zinc oxide one-dimensional nanorod over the things is a copper foil, and then overall this structure has been covered with the Kapton. See here, this is the overall device. Here they can covered with the Kapton. The brown color film is a Kapton. So after fabricating, we can see the device are highly flexible. So what will happen when applying the some mechanical force, it produces electricity. So this is the simple fabrication technology for the electric fabricate for the nano generator. It is a common mechanism. How we can apply? For example, here before fabricating, they have immobilized on the immunoglobulin. So this is the sum of the biomolecule we can immobilize or we can attach over the zinc oxide nanowire by different immobilizing strategies, by the covalent interaction or physical absorption or ionic interaction. Like that, there are different approach has been used for the interaction of some biomolecule or desired biomolecule in over the nanowire, zinc oxide nanowire. So what will happen without any immobilization of biomolecule over the zinc oxide nanowire, we will get a some output, electrical output by giving a constant mechanical force. Whereas after adding some biological molecule, or we can say biorecognize or bio recognize element or bioreceptor. For example, here if I add DNA molecule as a bioreceptor, what will happen after adding this bioreceptor as a DNA? When applying a mechanical force, that the electrical signal significantly altered, either made most probably decrease, because it is DNA molecule is insulating molecule, hence more possible to decrease the that electrical property. So further, when target molecule when interact with this one, what will happen? Further decreasing the electrical signal. So based on the ratio or based on the intensity of the electrical signal value, we can easily monitor how much the bioreceptor molecule has been coated over the zinc oxide nanowire and how much analyte has been interacted, uh, easily detect based on the intensity of the electrical signal. So here we can accurately detect the how much analyte desired molecule has been interacted with our device. Based on this one, we can use or we can apply detect the any type of molecules, either environment application or food related application or some biomolecule detections. For example, here further more detail, as previously as explained earlier, this is the nanogenerator devices. So here we simply just bottom titanium foil, bottom aluminum foil, or some foil conducting foil, then here titanium TO2 nanorod growth over the copper foil. This is the complete device. So what will happen? We are applying a mechanical force. It will give a some output in the form of voltage, which is called pure nanogenerator. It gives a particular voltage in the form of output when applying a mechanical force. So here further, here what will happen, in the second process we are coating some active layer. So this active layer is highly useful to attach the our bioreceptor, either aptamer or antigen antibody or DNA molecule or some nanomaterial. So this active layer, it may be different polymers, like we can use for the conducting polymer. So simply we can coat the conducting polymer by different approaches like chemical deposition or electrochemical deposition or photothermal deposition also possible by depositing the some polymer coating, as well as some amine based film coating, and also some carboxylic acid based film coating. There are different type of coating we can apply over the zinc oxide nanowire by using different approach. So like polymer or some functional group active organic compound, like that. What are the functional group in it? For example, here if you put NH2 or COOH, easily couple with some amino acid linked base using EDC NHS coupling reagent. And also, for example, glutaraldehyde, it is a die coupling agent. We can easily couple the both side, because glutaraldehyde it has a dialdehyde group. Both side it has a aldehyde group. It can be coupled with both amine group. So here, if we, for example, this is the glutaraldehyde dilinker, means it can be coupled with here this amino group, as well as this protein or DNA amine group also it can be linked. So based on our requirement, we can coat the this bioactive layer. What will happen? This is a pure nanogenerator. It produces some form of output in the voltage. So after coating the active layer, it is our assumption to increase the output, because if we use some conducting active layer, like for example some polypyrrole or polyethylene dioxythiophene, these are the highly conducting polymer, or polythiophene. These are the conducting polymer, can enhance the activity or conductivity of the zinc oxide further. So we are expecting to further improve the voltage of the device. So what will happen after that? This after coating the active reagent, further we are attaching the some bioreceptor molecule. Either here we are attaching the antibody in this schematic diagram. So same way we can attach some aptamers or enzyme or protein. Any biomolecule we can attach over the active layer. Even some material, nanomaterial also we can decorate. For example, gold nanoparticle or silver nanoparticle. Like that we can, some nanoparticle also we can deposit or attach over the active layer. So the active layer is specifically for attach some substances. Especially here we are attach some bioreceptor. So here in third things we can see that after attaching this over the after attaching this bioreceptor, here antibody over the active layer coated titanium dioxide, what will happen? This is the complete device. We have attached the antibody. So the first, this is pure device, next active layer coated device, further this antibody or bioreceptor attached over the active layer coated TO2. This is the third step. What will happen? Here the electrical output after attaching antibody significantly reduce after attaching compared to the first pure nanogenerator and active nanogenerator. Why? Because we are expecting the reason for reduction of voltage is due to the insulating characteristic of this antibody. It is significantly suffer the electrical conductivity between the copper foil and titanium foil between these two electrodes. So further, in the fourth step, this is the important step to monitor our aim to, according to this scheme, our aim to, this is the antibody, our aim to detect the antigen. So we know the antigen antibody reaction is a highly specific reaction. Particular antibody is specifically react with the corresponding antigen only. So antigen antibody reaction, high selective reaction, high specific reaction. So here the specific antibody antigen were allowing to interact with the fabricated device. So the antigens attached like lock and key method, it is perfectly bound with the over the antibody. What will happen further? Reducing the conductivity nature of this the RT layer coated TOU2. So what will happen is dramatically decrease the output voltage compared to previous three steps, because here more antigen also insulating characteristic, antibody also insulating characteristic. For example, here this based on the electrical signal compared to here, this is only bioreceptor attached nanogenerator device. This is antibody interactor. So we can see the clear difference between the voltage, output voltage from the nanogenerator after applying a constant uniform mechanical force. So based on this interaction, for example, here for assumption, here we are attaching a 10 antibody. So we are allowing only 5 antigen. So the electrical signal has a some particular intensity. Suppose if we are allowing 10 antigen, what will happen? Further reducing the voltage output of this nanogenerator device. Based on the signal strength of the nanogenerator, we can indirectly monitor how much target molecule like antibody has been successfully interacted or attached with over the antibody. So this is the main key idea for fabricating a immunosensor using the nanogenerator. So here what will happen, the concentration easily monitored or can be correlated directly with the voltage, output voltage from the nanogenerator devices. If output voltage is similar to here, means there is no reaction. For example, already I told the antigen antibody reaction is a highly specific reaction. So when mixing the sample like blood sample or some urine sample containing different antigen, if we are allowing, if it has a specific antigen, it will be bind. Otherwise, it will not bind. For example, solution A has been added. It has a different antigen, but it does not containing a specific antigen. What will happen? When interacting with here, there is no antigen antibody interaction. So what will happen? The similar voltage we will observe. So from this one, we can easily understood there is no reaction happen in the solution. Similarly, the solution B, it containing a specific antigen in this solution, particular concentration. So when interacting with these steps, what will happen? The particular antigen only it will interact. So what will happen? The original output signal from the antibody attached nanogenerator devices further significantly changes observed. Based on the signal intensity, we can easily confirm how much unlight molecule has been exist in the sample in the solution B. Like that, we can easily detect the any antigen. So this is a schematic diagram for how the nanogenerator can be useful for the measuring the sensors. So in the next example, this is for the DNA hybridization detection. So conventionally, DNA hybridization can be detected by the by using the probe this kind of probe single strand DNA has been immobilized on over the some conducting substrate and then interact with the corresponding complementary. Then we go to in presence of label or label free detection has been methodology has been applied to confirm the hybridization, whether hybridization occurred or not. Whereas here the same hybridization mechanism were involving. So what will happen? Similar fabricating technology in the nanogenerator between the bottom over the zinc oxide nanorod between the to connecting substrate. Here we are attaching the probe single strand DNA. So we all of you know the single strand DNA, always the DNA in our body, it has a double strand form. So when analyzing the some DNA hybridization detection and DNA mismatch detection, we are using the single strand DNA for our investigations. So what will happen? So here similar way, this is zinc oxide modified with the active layer, because already in the previous slide we discussed the importance of active layer. Similarly, the active layer here we can be modified with some polymers or nanoparticle. So based on the which method we are going to immobilize, because the DNA probe single DNA has been immobilized in different methodology, like polymeric entrapment method, or for example, here if 5 days modified with thiol group, the thiol group is highly reactive with the gold nanoparticle. So we can apply the gold thiol chemistry. So here also, if it is this active layer may be containing some amine group. Here may be 5 days group may be modified with the carboxylic COH group. So the amine group and the carboxylase group has been bind with some coupling reagent which is called EDC-NHS. Is a well-known binding reagent, can be used for the effective attachment of some biomolecules, variety of biomolecule over the some electrode surface. So this is general scheme. So here we did not mention any specific binding interaction. Our assumption, there are different approaches we can follow or we can use for the probe DNA attachment. The first one is like for example, if it is polymer coating, we can directly, if polymer has amine or COH, we can couple with, or if it is some functional group modified electrode like COH, NH2 or something, so we can directly attach using some coupling reagent. Or if we nanoparticle over the polymer, if we add nanoparticle, some gold nanoparticle, silver nanoparticle, means here we can choose the 5 days thiol modified probe single strand, because thiol we can highly tendency to attach the or highly high affinity interaction with gold or silver nanoparticle. Like that, there are different mechanisms we can use for the attachment of single strand DNA, probe single strand DNA over the active layer modified zinc oxide nanowire. So here what will happen? In this nano generator device, we are attaching the probe single strand DNA. After that, we are allowing the complementary target DNA. Okay. After that, we are allowing the complementary target DNA. So what will happen? So complementary DNA it is perfectly formed with a double strand DNA. So what will happen? Before attachment, only the pure nanogenerator, it will give you a particular electrical signal or a voltage output. After adding the probe single strand, significantly the output voltage has been altered. Most probably it will be decreased. So what will happen after complementary target DNA? We are allowing to interact with the complementary target DNA, which means it is adenine will be the corresponding complement. For example, here adenine means opposite thiamine. Here cytosine means opposite is a guanine. Similarly, there are all the sequences complementary to here. So the perfect matching will be occur. What will happen? Fully double strand DNA will form, followed by the significant voltage difference has been observed between this device and after hybridization occur device. Based on this electrical signal, we can confirm the successful formation of complementary DNA, successful formation of DNA hybridization. So in order to confirm whether it is truly formed DNA hybridization or some false outcome, so instead of this applying this complementary DNA, we can apply some non-complementary DNA. So which means non-complementary DNA means it is a similar base pair, or it does not interact with, cannot able to form a double strand DNA. So here instead of complementary DNA, if we are applying non-complementary DNA, what will happen? Here there is no double strand DNA formation. So automatically after this interaction with non-complementary DNA, similar same kind of property or electrode has been retained. So the electrical, when after non-complementary interaction, after washing the everything, when checking the electrical output, the electrical output after interacting with the non-complementary similar to that probe single strand DNA output, which means there is no interaction happen or no double strand DNA formed after interaction of non-complementary target DNA. So because it is non-complementary, it does not interact with. So from this similar voltage can be easily identified, can clearly confirm that the double strand DNA does not form with non-complementary DNA. So further here, if based on this device, we can easily the DNA hybridization occurred or not with the particular target DNA. Similarly, this device can be also applied for the estimation of mismatch sequences. So here instead of using complementary DNA, we can apply different mismatch target DNA like single mismatch, double mismatch and triple mismatch. But here definitely the complementary non-complementary can be easily distinguished, whereas in the mismatch how it will be work it is difficult to distinguish by this non-neutral device. So we need a further in-depth research or uh, in-depth research and further development to effectively distinguish a mismatch target DNA is highly important. So here we need a more detailed research to further establish the to effective detection of mismatch target DNA sequences. So based on this device, we can effectively confirm the effectively detect the non-complementary and complementary DNA sequences, whether the DNA has been occurred with the particular DNA sequences, hybridization occurred or not. So this is a simple process. Compared to conventional approach, what will happen? We have to perfectly clean the electrode and then we have to put the some bioactive layer or some nanoparticle or some metal based material over the transducer surface, followed by that probe single strain has been attached over the electrode surface. So the attachment also main important role to get a perfect signal. So here these are the process highly sensitive and repeatability is a really a task process. So after attachment of probe single DNA, we have to allow the either complementary, non-complementary and mismatched DNA. Then we will check the output of the either in the current or in the voltage or in the impedance. There are the electrochemical approach we are using to detect the different methodology. For example, if you use some voltammetric, we can measure the current. If you are using some impedance spectroscopy, we can measure the resistance of the interaction. If we are using the some potentiometric, we will monitor the potential changes. So based on the technique, we can output parameter will significantly change. So what will happen in conventional method? We need the signal amplification because the interaction may be very less. It's difficult to measure by the electrochemical method. So we need some redox indicator either in the measurable in the measured solution in the electrolyte solution, or we have to attach some redox label or redox indicator over the either probe DNA or target DNA for the effective hybridization detection. Whereas in the electrochemical approach, we can possible to detect the mismatched DNA sequences also. Even single and by and triple mismatch also can be effectively detected based on the electrochemical approach. But only thing we have to in presence of redox probe or redox indicator has been exist in the solution or in the modified target or probe DNA. After this interaction, we can effectively confirm the successful formation of hybridization occurred or not can be easily detected by the electrochemical technique. So here we no need to use any redox indicator or redox probe over the solution or in target, because with this all the reaction we can be performed in a solid state stage. So we can measure the this device effective for the discrimination of the sensor subset has hybridization occurred or not. But the mismatch based on this device, it has a different task. So we need a further in-depth research to effective discrimination of or effective improvement of this non-generator based device for the detection of even mismatched target DNA. So in the next lecture further we will continue what are the advantage or what are the future direction based on these non-generator sensor devices. Thank you.